The last topic of this course is known as Rayleigh's criterion of resolution. It addresses the question, when can you see two objects, such as two stars in the night sky, as being two separate stars as opposed to one fuzzy star? The answer comes from the limitations of the human eye. If you're looking out there in the sky, you're not going to be able to see more than about 4,000 stars, assuming the night sky is perfect, free of any atmospheric effects, and your eyesight is perfect. 6,000 stars, I guess, is the limit for people who have tried to do this at proper latitudes. Now, if you want to increase your D, the amount of light you get in, you will of course use telescopes, and the bigger the telescope, the more the D. The criterion of how you can see two things separate, whether it's your human eye or a telescope that's doing the viewing, is that the diffraction pattern of light that's created at the instrument level should be such that the primary diffraction hump maximum of one object should occur over the minimum of the diffraction hump of the other object. If it's any closer than that, then you will not be able to see these two objects as separate. You'll see them as one hazy blob. If it's exactly at the Rayleigh limit, then you can just barely resolve. So this is sometimes called the condition for barely resolving two objects. Now, if the minima is well separated from the maxima, then you're resolving it really well. You won't be able to see this effect in any real traffic, but if you try to see this from an airplane, you can see a pair of car headlights from an airplane initially look like a motorcycle headlight, as though the two headlights are merging, and as the plane descends, then you can see that these headlights suddenly split and you have two beams coming out. So what you thought was a motorcycle is in fact a car. That's one example of this Rayleigh resolution in action. The theta critical is called Rayleigh's angle. Let's solve for it. Sine theta critical is going to be 1.22 lambda upon d. Now, for most applications, theta sub c is really small, so the small angle approximation can be used. I can use sine theta sub c is approximately equal to theta sub c in radians. That's almost always true in applications because astronomy deals with incredibly long distances, and these angles are a few minutes of an arc or a few seconds of an arc, so that condition is amply met. In that case, we have the formula theta sub c equals 1.22 lambda divided by d, where lambda is the wavelength of the observable light in this problem. Now, this is sometimes called the resolving power of something. The resolving power of a human eye would be 1.22 times the wavelength of normal light, which is about 550 nanometers, divided by the diameter of the pupil, and that's called the resolving power in radians. In problems, how do you use this? Let's, as an example, try to find out. You go out in the night sky, it's a beautiful day, and you're seeing the full moon, and you start counting the craters, as our man Galileo did. What is the smallest crater on the moon that you can see with just naked eyes or bare eyes? Well, that can be found using the Rayleigh resolution criterion. Your eyes are located here, and assume that you're not using any telescopes. So all you're doing is staring at the moon. Now, when you look at the moon and you're looking at this crater, let's assume now that this is not the moon, but this is the crater. The moon is something big. So this is the crater you're looking at. Let's draw this bounding tangents to the diameter of the crater. Strictly speaking, this is not the true diameter, but the distance between the two tangents, but we don't worry about such subtleties. That's the diameter d. And so what you have to do is somehow figure out what that is. Well, this can be done in a pretty easy way. The distance between the Earth and the Moon is roughly 60 Earth radii. That's how I remember it, because the Earth radius is easy to remember. The Earth radius is 6.4 megameters. So this result, by the way, was known to even pretty ancient astronomers like Hipparchus 2,500 years back. And certainly was known to Newton and helped him discover his law of universal gravity. So you have this basic diagram. You're looking out into the sky and the moon is bigger than this, and then you look at the crater on the moon and you want to be able to see the crater as a crater and not just homogeneous part of the moon. The Rayleigh's resolution criterion can help us here. Theta sub c is 1.22 lambda over d at the level of the human eye. But theta sub c is also equal to a geometrical fact. If this distance is huge, and it is, compared to the crater diameter, then this distance can be thought of as the distance of an arc of a circle. For an arc of a circle, we can use the arc geometry. The arc geometry states that the arc length S equals the radius R times angle theta. In this case, the arc length can be approximated to be the diameter of the crater itself. In fact, it's actually a better approximation to the diameter than this distance between the 2 points of tangency. So without any reservations, let's write d equals R, which is 60 Earth radii, times theta c. Now I have an expression for theta c, which is d over 60 Earth radii. But that's also equal to 1.22 lambda over d by the Rayleigh resolution criterion. So I have equated the two expressions for theta sub c. This part comes from the pure geometry of the situation, and this part comes from the physical optics. In application, you always have to play this double game of setting a geometrical side of things equal to the physical optics side of things. The last step is to actually solve for d. So d is equal to 1.22 lambda times 60 Earth radii let me make sure I did all this right. And then divided by d. The units have to come out in meters. Lambda is in meters, RE is in meters, d is in meters, so you get the right answer. Now the big question is what lambda to use. As you all know, the moon does not produce light of its own. The light of the moon is actually sunlight reflected off the moon. So for the most part, the lambda is going to be something like the wavelength of visible light at the peak, which is yellow-green. So we can call lambda 550 nanometers. So I have d equals 1.22 times 550 times 10 to the minus 9 meters times 60 Earth radii, and that's 6.4 times 10 to the 6 meters divided by d. That's a big question. What is d? If d is large, little d is small. That makes sense. If you're going to be using a gigantic telescope to see the moon, then d will be very big. That'll mean little d is going to be very small. You can see minute craters, perhaps even the flag planted by the astronauts. So this d, unfortunately for the human eye, is not very big. Even if you're staring in perfect darkness, the pupil does not become that big. So let's just put it as 1 centimeter, which is really a wide-eyed person. So that's going to be 10 to the minus 2 meters. So let's see if I can do this by hand. 1.22. I'll talk about the irritating factor of 1.22 shortly. So that's 5.5 times 10 to the minus 7, because I've borrowed 2 zeros there. So let's keep that in mind. That's going to be 6 times 10 to the 1, which I'll borrow there further. So that's 3 zeros I have borrowed so far. Times 6.4 times 10 to the minus, because I've borrowed 3 zeros, 1, 2, 3, that becomes 10 to the minus 6, times 10 to the 6, they cancel out nicely, divided by 10 to the minus 2, which I'll just keep here. Now 6.4 times 6 is about 40. So 40 times 5.5 times 1.22 is about 7. So 7 fours are 28. And then I have times 10 squared up here. I may have made some error. This is different than I remember. So 40 times 7 is 280. That's what it is. It's 280 times 10 squared, and that's 28 times 10 cubed. So it's about 30 kilometers, give or take. That's a pretty huge crater. 30 kilometers is about 20 miles. So you cannot see a crater that's smaller than 20 miles in diameter if you look out into the moon, even if you have perfect eyesight and everything about you is perfect. This might seem a little humbling, because if you have perfect eyesight, you think you should be able to see anything. But if you have a crater that's 22 kilometers, you'll just see it as the plain surface of the moon. Okay, what is this factor 1.22? That comes from the special shape of the diffraction hump for a circular aperture. Now, for the straight slit, that turned out to be the sinh squared function. This is like the three-dimensional sinh squared function. So the first minima doesn't occur at multiples of pi, but at some zeros called the zeros of the Bessel function. So the 1.22 comes from the zeros of the spherical Bessel function. This is already pretty deep mathematics, and so I won't go any deeper into that, just to tell you that that's where the 1.22 comes from, and you should not worry too much about it. Just use it in the problems, and you can find out all kinds of interesting things about the limitations of even the best telescopes and so forth.